Well, thank you again for the invitation, and I think Juan has done a really, should I do something? A really nice proposal to try to have a more good Blackboard talks, and I personally enjoy them more than slides talks. But I've been given nothing but slides talks recently because they seem to be, the standard these days. And because of that, I've forgotten how to measure time when you're on the board. So I ran out of time last time. And I did want to continue because the punchline was really in the last part. So I do think there was something missing. So I'm happy to have this opportunity. But I also got some complaints. By complaints, I mean complaint, and that the Goodstein process was still too complicated. And I think that is not the case, but I think I did make the mistake of focusing on giving formal definitions last time, as opposed to just kind of explaining stuff. So what I'm going to do is not really give any definitions now. There will be what was this Trump saying? We don't have a plan, we have prospects of a plan? We'll have those. So in the original Goodstein, thanks to Oriola's talk and addresses. Oh, by the way, I am sure you're all feel very fortunate that you came here this week for one Goodstein talk, and instead you got 4 and a 12th. So that's why this is 4 and a 12th. So, fortunately, I can go a little bit quickly over some details, but the original Goodstein, you start with base 2, and if you have a number like 41, when you write it in base 2, it will look like, well, first you write it as powers of 2, which would in this case be 32 plus 8 plus 1. And then you also treat this the same way. And very important, these ones, since they're smaller than my base, they're just digits, they just stay there. I could have more digits in principle, but now it's base 2. And that's it. So the idea for this extended version was that now we have a family of bases, and each base is used for writing numbers of a certain magnitude. So in this case, this is base B notation, but this is not a capital B notation. Why is that? Because this is greater than 6. So the appropriate base to use here would be 6. So instead we write 41. So that'll be 636, 6 squared, plus 4, plus 1. I'll write it like, oh, I'll just write it like this, I guess. Okay, now these digits with respect to 6, themselves have a base 2. And in this case, I just stay the same, but 5, I write it in base 2. So 6 plus 2 plus 1. The 1 being smaller than the smallest base is just a digit again. And that is base B decomposition. So that's one ingredient. The other ingredient is the upgrade operator. So let's say that C is sure. 6. Yes. Yes, maybe that would have been good to have in the example. Yes, exactly. Right. So if you want an example like 6 to the 6 times 4 times 5, that would become 6 to the 6 times 2 to the 2 times 2 to 1, right? All right, so now we have a new base hierarchy. That's what I call these. The only rule is that if B is non-empty and totally ordered by divisibility. So every larger base is a multiple of any smaller base. It could be either, it doesn't matter. In the paper, I am precisely answering that question. In the current preprint, it's mostly handled as infinitary, and there's a little section at the end that makes it finite. Today, I will try to keep it finite. You don't need it. Infinite makes as a mathematician working with these, it's better if they're infinite. But for independence, they could all be finite. So our C will be this. And I'll throw this one in just for fun. 30 to the 4. Okay, so we want to upgrade 41 from base B to base C. Sometimes I'll omit these. And I gave a formal definition last time, but it's one of those things where it's a simple thing that's hard to write precisely formally. So step 1, upgrade. I'll write it like 6 digits. Because my base is 6, so everything below 6, even though I'm writing it in base 2, it's still considered a digit, right? And at this point, nothing special will happen. These the 2's just become 3 because it's the lowest base and so forth. So this, you have to think of it recursively, but trust me that and in this case, this will just happen. You would expect. Now that is bad for several reasons. First of all, 6 is not one of the allowed bases to begin with. But for example, I have a digit here that's bigger than my base, so that's bad. So step 2, replace 6 by least suitable C and C. What do I mean by that? Well, I'm going to view that base as a variable. Well, I'm upgrading to base C, to base system C, to base hierarchy C. Base hierarchy C does not even have a 6 available. So I have to use these, right? So that's thing 1. There's more things wrong, but they'll come up again. So I'm going to view the base that I see as a variable. And I want to find the least good value, the least value that kind of makes sense. So we try 3. That's our smallest base here. C equals 3. And you get 3 plus 3 plus 1. That is bad because the digits are already bigger than the base. So that's bad because 3 is less than. Okay, so we try C equals 30. I feel like this is. Yes, so I'm missing the 180. Thank you. There was a 180 here, and then there's. So C equals 30, you get 30. So this kind of looks like a reasonable notation. The only thing that is that this is less than the next available base, so that's bad. Okay, so I try C equals 180. And that is good. Why? Why is that good? Because that is less than the next available base. and my base is large enough to be bigger than the digits, and that's it. That's the base C. Yes, that's because I forgot that thing about the alligator wanting to eat the bigger number. But precisely, it's bad because it's too big. And then it was good because it's smaller than the next thing I put on here. And that's it. So.
But you want it to be bigger than.
It is, but the base is 180. Right, but you want it to be bigger than its base. Bigger than 30. Not bigger than the next base, which is the one that you're not using yet. No, you want it to be as small as possible. But the rule is that bases are, what is the base? So base, assuming that is the least, is the max. Right, so the base is something smaller. You use the biggest possible base, but it has to be smaller than your number. The exception is that things that are below the least get the least because there's nothing else to give them, but generally you want this. So this number would be assigned the following base, and that's why it's bad. All right, so that's it. That's what you do. You follow these steps. And the theorem is that... Yes. Yeah, so this has maybe, it would be nice maybe to put a little square on this. So this is being treated differently because it is the value I'm testing. And these are digits that are already fixed and static at this point. Okay, so the theorem is that if base, as for this theorem, they could be infinite. That's fine because this theorem holds always. With a condition, it's such that a good professor EI, and I will get back to this. I defined it last time, but I don't. I'll get back to it in a second. Then for all n there exists an I such that gi is equal 0, where g I might use a notation, which is just shorthand for upgrading from the base I have now to the next one. So this theorem just holds always, as long as there's some regularity on the between one base and the next, and and what does regularity mean? So we will see it as follows. When I have this base B and this base C, I want to imagine the C is sort of being constructed as I also construct the upgrade. Here's B. More like internet square are bases, and I want to construct C, right? Ourselves more space. So So what rules do I need for C to be a good successor of B? What does it mean? First of all, if I have these digits at the bottom, in this case it's just 0 and 1, but there could be more, then the upgrade doesn't do anything to them because there's no basis to change at all. I don't want any basis to sneak in here. So the first base I see here, it could be 2, that's fine, but I could also make it, I could make it huge. For sort of cultural reasons, let's just make it 2 plus 1. So C is a good successor of B if it could be equal, that's fine. What else? So then I have the 6 here, right? It's the next base. And I do want the upgrade to be monotone. So, and I do want bases to go to bases. So I need some other base somewhere. I cannot just stop here. I need to assign this a base. So what do? I look at 5. I map it. 5 would go to, 5 is 2 to the 2 plus 1, so it will go to 3 to 3, it will go to 28. And here's the rule that when I have a base, I don't want a big jump. I go to the next possible value. If my base is 3, and my rule is that bases are multiples of each other, the next possible value is 30. Right? So, and I already hinted at this. If I deleted this, the upgrade would not be total because I would have nowhere to send this. You don't get it for free. Okay, now I've taken care of my bases, and now I could go wild. I could add more stuff. There's many places where I could add stuff. The rule is that you never add stuff below what you've added. So just for fun, we added 180 and 180 to the 4th. But this is how you construct a new successor, good successor. You do it inductively. Whenever you could do some extra things if you want, but when you reach a base, you always raise its predecessor and then add the next possible value as a base. And as long as you're doing that consistently, you will get a good successor. So these exist. No, I could actually have added, and we will. We will. No, oh yes, exactly. Once we fix, we fix. So it's like when you do recursion theory, a lot of times when you're building a set, you want the 0, 1 information to be fixed, not just the 1 information. Right? So it's kind of this flavor that once I got into a certain height, things that are out. But I could do more stuff on top. And as long as I make sure to always give my basis a value, I could go wild and add all this crazy stuff. Which for infinite bases is maybe a bit more subtle, but as long as the two bases are finite, just take care of your bases and then you could add what you want. If you stop at some point, you will have all these properties.
So for infinite bases, you have only the choice to work.
No, well, we will see. I could perfectly have.
Decided that the first element, then the second element.
No, I could perfectly have added something here. That's fine. But then what happens? Actually, let's just do another. Let's do C prime. Let's send this guy to. Let's keep it 3 to not make things too different. And let's say we want to add. We can add 6 actually. And this is a little bit of a. And that's going to be a little bit sneaky because now the temptation is to send 6 to 6. But we no longer can do that because if you look at 5 already went to, it wants to go to 28, but it can't because it goes beyond it. So now 5 has to go to 6 to the 6 plus 1. Right, so 5 is here, goes 6 to the 6 plus 1. And now this is a multiple of 6, so I guess the next base has to be 6 to the 6 plus 6. So you could go wild as long as whenever you reach a base, you make sure to add the next thing. Otherwise, and to follow the divisibility rule. Otherwise, yeah, there's a lot of freedom. And we will use that freedom because we need it for the independence part. Okay, so now I will make use of what Ariola did. Look there. And talk about very quickly. And this is a little bit blasphemous to anybody that's done Goodstein. So you remember, we prove the determination by an ordinal assignment based on the theta function. Now I'm going to prove independence by using a completely different assignment based on this lower drawing function that ultimately gives you the same ordinal. And I don't have to do this, but if I could give a single optimal ordinal assignment, but it is very messy. So instead I'm going to use this trick. And this is the slope psi. So remember that, for example, if I have something like this, the star here, that's its largest countable coefficient, so in this case, it would be gamma 0, right? That's a psi function, exactly the definition we're all used to. Actually, it is exactly equivalent to the very complicated definition people like to use. The only difference here is that I'm not forcing this to have a principal values, so this takes all the values. But if I made these be principal values, this is exactly the usual psi function. And Ariola already talked about fundamental sequences, and we're going to use the following facts that, so the definition she showed, whenever you restrict operations, these types of functions have a nice property that fundamental sequences specialize. So define more or less before. Define you take psi, you take the 1 fundamental, the 2 fundamental up to n, right? And then because if psi is less than the ordinal less than this ordinal, then you know that eventually this will reach 0. So h of psi is the L such as 0, and we're going to define f of n to be h of psi of omega omega. This is, and then fact. AP, or your favorite Howard-Bachmann strength theory, does not prove that F is total. We're going to use that. We're going to use a slightly stronger fact that if I take any function any computable function that grows faster than this, then KP does not prove that that is total. So, same time, right? So, what is the idea? So we have, remember that back in the day, we defined this ordinal assignment, which had kind of the form where this was the uncountable base omega 8. And this was sort of a correcting factor. So the correcting coefficient was to keep monotonicity, but otherwise you took an ordinal, a 5 over there, 2 to 2 plus 1 would go to this, and then this would be applied theta. And maybe I would add something to make sure that I have monotonicity. So now I'm not going to use that assignment anymore. And so fact, let chemical base hierarchy. So remember, this means that it's a family of base hierarchies, that each one is a good successor of the previous one. And UI from N to countable ordinals, well, I guess. Such that, and this is when we're gonna get, we actually are going to cheat, and we're gonna get around the Bachman property, and the only person that's gonna understand why that's important is Gorilla. We don't need Bachman property, we do this trick. We actually need the Bachman property for this part anyway, so. Such that for every n, for every I, n greater than 0, there exists m less than the upgrade of n, such that the order type of m is exactly equal to the order type of n, and I apply the fundamental sequence, and I think I needed an I plus 1 here. Then, and then for every I, di, b, so what am I doing here? What should I erase? I guess the first one. What am I doing here? So you think of Goodstein as being a sequence of copies of the natural numbers, each equipped with a different notation system. You start with n, which is, well, let's say that ni is the Goodstein for b at n. You start with some n0, and the upgrade will take you to some n1, but there's some m1 that has a property that its ordinal is exactly, this was psi 0, that's psi 0. Okay, and then, so actually N1, maybe I'm doing this, you go up, you go down a little bit, that's N1. Because I only subtracted 1, M1 is less or equal than N1. This wouldn't work if I subtract a bigger number, but I'm subtracting as little as possible, and this M1 is guaranteed smaller than N1, so it is smaller or equal than N1 minus 1. Okay, so then Goodstein takes me up, takes me down. There's a sign for that. And then what I do here is I go to some M2. That is, well, first of all, if I just did the base change here, base change is still monotone on numerical values. And that means that there's an M2 here, which gets psi 0. Let's start using this. And I keep doing this. Every time Goodstein takes me somewhere, this guy at the bottom is just always going to be underneath, but it's taking exactly the ordinal value of the stepping down process. So the only way for this to be 0 is for this to also be 0, and that's only going to happen if this is 0. So that's... No, the double brackets mean what you just said. So yes, 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 yes. Great. Okay. So now I might be. I didn't finish early. If I finish early, I'll just finish. So let's do an example. The critical example is, as we all know, psi omega to the omega. So the critical example of fundamental sequences is a case where you have a psi applied to something of cofinality, capital omega, uncountable cofinality. So let's calculate this, and the way you calculate these is that you have to do all the previous ones. And the reason we start at 1, call this psi. The reason we start at 1 is because we sort of need this auxiliary value that will not behave very well, but it's still useful for it to be there, so we start at 0. Very good. What do we do here? What we do is we take the ordinal we had, we take its limit part, and we put our previous value. That's going to look like psi omega 0, which if you look at our definition of psi 1, that's going to be 2. 1, 3. 1, 3. I went through. Yes, let's go. All right, same pattern. I put this here, and I stop here. As you keep going, you start to get this thing just kind of embedding. So what we're going to do is take this, that construction there, and force it to somehow majorize these fundamental sequences. So which is probably my best? Maybe I think this is the best board to erase right now. So goodbye, this board. So we're going to do a minimal example. It's just 2. But we're going to now define, I'm only going to define the, I'm going to define an initial segment of this. You might have to go up a bit more, but I'm going to define how this begins to be constructed in such a way that it will majorize fundamental sequence. So what do we do? And this is where you start to see how you can really go wild with the base hierarchies. So as usual, we have to respect these. we almost always will add one to the least base. You need to add something. 1 is equal to something. And the number I want to look at is 4. Now we'll put 4. Oh, I did not define this. So what is this simplified ordinal interpretation? It's going to follow the same pattern as O, except that it's going to take the psi function, take the uncountable version. The U just means I'm using psi instead of theta, and there will be no correcting term. So this is going to be highly non-monotone, because you could imagine that if I'm over here at 5, that has a stack of an exponential stack, is going to get mapped to a big ordinal, and then 7 is just 6 plus 1, get mapped to a small ordinal. So I lose monotonicity. So I have to be really careful to here dig out an image of the fundamental sequence while avoiding all these bad stuff. Okay, so where does 2 to the 2 want to go? This is not a base, by the way, it's just a number. It wants to go to 3 to the 3. 27, right? But we're not going to let it. We're going to decree this to be a base. What does that do? So if I raise this to base 3, I get 27, which makes this a bad base, so I have to now use base 27. But we will not let 2 to the 2 rest, because now it wants to go to 27 to the 27. And guess what we're going to do now? Of course, decree it to be a base. And then I'm running out of space. Call this M. I'm going to do I do one more? Hold on. Done. So B plus I, at least to be 3, 27, 27, 7. And it could have more stuff eventually, but this is it will not affect anything that happens up to here. So now we let it peacefully go up to M to the M. All right, so the claim here is that I could always find a smaller number which has the values of the fundamental sequence. And in fact, a more specific version of the claim will be that I could find all of these guys, and each one of these will be below a respective base element that I added. So I need to erase. So okay, I want some number that looks like psi 0, which is 0. That's a no-brainer. 0 looks like 0. Okay, so then the next element of the fundamental sequence is 2. So I want a number that looks like 2, and we have here 2 available. Okay, so now's where the interesting part comes in. Now I want a number that looks like omega to the 2. So that means I take my base, which will be reinterpreted as capital omega, and I need a 2 on top. So here I have available, here somewhere, between 3 and 27, I have 3 squared, which looks, what does it look like? It has a psi, and the base gets replaced by omega, and the digits get replaced by their interpretation, because it's down here, it just looks like a 2. Good. And what's the next one? I need something that already looks like that, and I need the base underneath. So what looks like that? Well, I already did find 3 squared. And I know that maps to this ordinal, so I just need to put this on top of a base. I put 7. The 3 squared. And that, maybe I'll zoom in on this. What does that look like? Well, the rule is I take the main base, I put up psi, the base becomes omega, and then when I have smaller things, I recursively do the u thing. So that means I put up psi, the base becomes an omega, and then 2 will just be 2 because it's small, so that's it. And yeah, I will always have an image of the fundamental sequence between each base, between the respective base that I added. And by just obnoxiously, blocking guys from, you have to at some point let them, but by just blocking things from their desired upgrade a few times, you're effectively getting this equation. So here, well, yeah, so that's so here. So the E. Oh, okay. So the one last observation. If I start with 2 to the 2 to the 2 to the 2, this will go to omega, 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 omega. So in general, I have a tower of n2s. That's going to u n is equal to omega n. So from these considerations, we obtain that if G writing. So if this is the least, I'm going to switch to another board. Erase this. Here, well, this is more like a proposition. If G n is the least I, such that G I So theorem 1 was a termination, and so if I take such a tower and I define B using this basic recipe, then this function is going to be this fast. Everything here is computable, so you can use this general result that no computable function is provably total than this. So here's where we get our independence. So yeah, thanks for the extra time, and so every time you get a number is critical if it is a multiple of its own base. Every time you get to a critical number,
Power, you mean
multiples enough. You could restrict it a bit more, but you could do it at every multiple and it'll work.
you mean numbers?
No, so for example,
No addition.
no, just like if your 6 is 2 to the 2 plus 2, you could add a base here. But think about it, this becomes omega, omega plus omega. So you're going to be at the critical case of the fundamental sequences. Base is 2 and 6 is a multiple
Oh,
of.
okay, it's a multiple.
So whenever you get to a number that's a multiple of its own base, at stage I, you're going to add I bases. What are the I bases? Where did I go? Here it is. What are the I bases? Well, you try to raise a base with what you have, you'd make that a base. You try to raise a base again, you make that a base. You do the I times, and then you let them go, and then you keep going for the next numbers. Don't add a base. Well,
All those in general.
at any fixed moment, I know how to raise things, right? I could block them and force them to go somewhere else,
You don't have to raise.
but I have a current candidate for the raise. When I'm not at a multiple, the current candidate is going to be the final value.
Add new number.
But I'm never going to add numbers to the left side. I'm creating something from scratch, only on the right. No, in fact, for the final theorem, the first base is this. No, they're not increasing. No.
Oh,
So
so you-
in the final construction, the first base is 2. This is going to be 3, and then some more stuff. So I guess 3, 27, 27 to the 27, until you get tired. These all come from 4, which is the first critical number. The next critical number will be 6. When you treat 6, this base is already there, so 6 will already begin really high up.
well, but B2.
So you stop this at some point. So let's say your Goodstein process started at 4. So that means you're never really going to bother with these guys. So you could just stop it here. You don't. So you only have these bases. So now that you have all these bases, you do the process for all these numbers, and the last base you're going to add would be basically for this. You're going to do the process.
Sorry, what do you do with all of these?
So let's maybe it's easier to just give an example where I have 2 bases.
I think I would.
All right. So you have any B, whatever.
BI, sir, BI.
Right, exactly. So what's the formal definition? This is going to be the union of some C n's. And the n means that I got this from the number n. It doesn't really, it's usually going to be a much bigger set. So, and it's not always going to increase. Then Cn is equal to up to here, the only base you have is the least one, which is 1 more than what you had before. So otherwise, n is greater than min b. Let b be its base. And you have 3 cases, which is In this case, so the construction bases are supposed to be tame. They're just kind of helping us there, but so you don't want it to do anything too exciting. All you're going to do is add the next possible thing you could add. Cn is C union, bless you, so I'm K, where K is the least multiple. So now we're going to have to get some of the base with respect to Cn minus 1 of the upgrade of n minus 1, such that, hold on, let me just finish this, K is greater than n minus 1, right? So in this case, it's what I said at the beginning. If you just want to create a good successor, you could just do these two steps. You only add this next possible base whenever you reach a base, and that's it. You get a good successor. You will not get independence, but you will get a good successor. Okay, so now. So there's two options. You can make this an infinitary construction and just go all the way. But you want to imagine these numbers being on the domain side, right? They're base B numbers. And you could either stop somewhere because you're not interested in more values. If for example, your Goodstein process starts here, you can stop here. Or you could just do it forever. Either way is fine. Let's say, yes, it is computable. I haven't finished telling you what you do, but so the critical case is when you have something that is not a base, but is a multiple of its own base. That's like the 2 to the 2 example. Actually, let's just go here. What do you do? First, you do what you would have expected, which is you take that E. You take the largest base you had available at this point, 3 in this case, and you try to raise it. Actually, let's call this Z0 and define the j plus 1. You're going to take whatever dj was, you're going to replace the base of n for that in n. And then Cn is Cn minus 1 union. I don't have d0 because I was already there before, but I add these I new values. So in this case, this is D0, it was already there before, D1, D2, and you could go as far as you want. You have to stop somewhere, because if you don't stop somewhere, what you're doing is that the upgrade is no longer well defined, but as long as you give it some breathing room, you're good. And that's it, that's the construction. It is, but then
But also, if you do it in this infinite setting, because
well, if you represent it as a set, but you could represent it as a range of a computable function, and you could make it pi 0 2. And
the general set.
yeah, but then the n is finite. Well, so the original theorem looks pi 1, 1. That would be equivalent, well, equivalent, morally equivalent to this, to the version of Goodstein where the bases are arbitrary. So the adversary at each point chooses a base that is larger than the current base, and you raise to that base. That becomes a pi 1, 1 version of Goodstein. That's equivalent to well-foundedness of epsilon naught. Yeah, I assume so. Yeah, it should be. So since apparently I'm the last physical speaker, I think